Go away.
Go.
Go. All right. We're going to go ahead and get started. My best to keep things in line as we go. But I will let you know I am balancing windows here, trying to make sure we can see it all. So I ask that you please bear with me. Others will probably join as we continue to go, but we'll work it out as we do. As I stated before, for those who might just be coming in, there is a slight delay. So please type your questions in, type your questions in, and I will try my best to get to them in an orderly fashion. Now, I had a couple of questions that came in. Uric so far about electron affinity and Coulomb's law and looking at the trends overall. So I went ahead and took some time to pull some questions together, some of the graphs together so we can use that. And at the same time, we also are going to take some time and look at some of the questions I assigned today. I won't lie to you, it feels kind of weird not being able to see people's faces or hear people's voices, but we will do what we have to do to help out, making sure that you all are ready for tomorrow's exam. So let's go ahead and get started. The first thing I want to look at are to behave, and for the most of these patterns, why these patterns exist and where they're coming from. So, and the first one we're looking at is actually now, if you remember, we talked a little bit about electron affinity today and things. We noticed that are down here in this, trying to understand why is it that drop in energy, or this big increase in energy when we were looking at electrons. Look at what screen, and I love to use oxygen and fluorine as an example because they make things very clear in terms of the actual. As we take a look at oxygen, we have 8 electrons represented, but we have these two spaces, some electron there. In other words, there's some imbalancing. There's an imbalance in terms of this is some other examples, and I'm talking for the electrons filled huge drop in energy. Then fluorine means that one electron have a stable number is going to release a whole reaction, go back to that where the nucleus benefit from it. So as we continue to look at affinity, here there was a question that was asked, increase going up to, and that is now we have. So while we look at the electron arrangement and the full orbital nucleus, is while the electron were very big. I'll just make sure if you can't do this, but I might Okay. Pardon me for. Hello, hello. Are we working through here? Okay, wonderful. Now that we have everything settled, um, we were speaking about electron affinity and the orbitals in their arrangement. Question for those can't hear at all now. Oh wow. Boy. Okay, Lauren has it working. For those others who typed in, or do you have your sound back now, or okay, okay. So it looks like we're back on track now, and what I'll do is I'll go over briefly again the whole part about the trends. We're going to talk mainly. I have a couple of things up here about ionization energy and electron affinity. So, so good. All right. So again, the idea that we're working from here is that with our different elements, they're arranged in such a way that we can tell what the properties will be. In the case of what we're looking at for the atom, we know that the electrons are arranged in a certain fashion. We know that we have our S, P, we know we have an S, right up top, P, D, and F orbital. Now, for each of those orbitals, though, they're of energy 1, but also all around the atom. These shapes are not always symmetrical. What do I mean? Well, I'm going to go to a blank slide. If I'm looking at this is my atom. Sorry, I keep having to do this. If I'm looking at this is my nucleus, and around it I have an s orbital, which is more so like a ball, a sphere, and then we have this p orbital that's coming off the top. Within this space, I may have two electrons once everything is filled. Now, the issue with this is these electrons are most likely to be found in these areas. So at any point, I could actually have it where, let's see, oops, didn't allow me to erase, but that electron's not actually there, but both are on this end of the atom. This is going to cause the atom to be off balance. It's going to take more energy and more attraction from the nucleus to try to hold it together. So, the more stable we have it, including those other arrangements. So this is one p orbital, this is a second p orbital, and here's a third coming off. If we have electrons that are balanced in each of those places, what's going to happen is it's going to be much easier for this atom to hold on to everything. So the goal is to get to the full orbital. That way everything is what we call balanced. Now, when we go back a few slides and we look at oxygen, oxygen is not very balanced. Right now, we have a couple of electrons in the p orbital, but in one of them I only have two electrons. The other ones are single, so they're moving around a little bit more. For that reason, the nucleus is almost like the nucleus is working harder. Now, I know that the nucleus itself doesn't have the capabilities of working, but the attraction is a little bit more strained. As we get closer and closer to filling it, we're going to release a lot more energy because it becomes a lot easier for the atom itself to be balanced. The electrons aren't throwing it off course. That way, once we add in this last piece to make our fluoride ion, this is now a full and stable electron. So what it's going to do is it's actually going to shoot off a lot of energy. And this is going to be stored as potential energy, chemical potential energy. As I look at even ionization energy, this is the goal. When I take away electrons, I'm not just taking them because it's the thing that needs to be done. It's all about filling a valence shell so that so we can release energy and so we can be more stable. Does that make sense in terms of what we're discussing? Now, I've yet to cover the part about Coulomb's law, so I'm going to make that covered. All relates back to the structure, filling the orbitals, the energy. Pausing for just a moment. Okay. So far, I have no questions. Once you type in questions, I guess I'm there. Now, the next trend that we're going to analyze a little bit here is ionization energy. First, ionization energy at that. So, if I'm taking a look of ionization energy, the amount of energy it's going to take for me to steal away an electron. The more balanced, or the more the orbital. Now, the question then is it so difficult to take away the electrons? Look at what happens in two directions. If we look at what happens in terms of the group, we always say that it decreases from top to bottom. Now, as we go down within the group, it's going to decrease. Why? Well, each row that I go down in the periodic table is equivalent to an energy level. And as we discussed the other day, these energy levels are at actual fixed distances from the nucleus. But we're going to get further and further away. The relationship between distance and attraction is inverse, meaning as the distance gets, and because that attraction becomes weaker, that's going to make it easier for me to take the electron away. So if I'm looking here at the bottom of my graph, I notice that I run into lithium, I look at potassium and sodium, I look at even looking at my um, alkaline earth metals, I'm also noticing that those are a little bit towards the bottom. Now, some may ask the question, not ask the question, but note that there is still a little bit of an increase between. Remember, a stable orbital, or a full orbital, is going to require less energy. So, if this is going to require less energy, less energy, that means it's going to want to stay into that configuration. Um, have a question regarding drawing the orbitals. Are we talking p orbitals? Or are we talking about the rings here on the top of the screen. Again, sorry for the slight delay. I'm trying to make sure the questions get answered as they come up. Okay, so the rings here at the top. In setting up the rings here, or at least I'm going to try to explain based on distance. Yurik, please let me know if this is what you're talking about, or if you come up with anything to make it more specific, please let me know. So, as I go further and further out, we know that there are a total of 7 different energy levels for each atom that are available. Now, does that mean that we actually have electrons in them? No. It just means that there's the option there that space is available. So, as I continue to add on energy levels and get further and further away from the nucleus, I'm going to then start to feel a lot less of my attraction. Again, think of it like the magnet that I usually hold with the board. The closer I get to the board, the more attraction I'm going to feel. But because that magnet isn't strong enough to feel or to have that strong of an attraction to the board at long distances, it's going to become weaker and weaker and weaker to the point where I almost feel no force at all. It would be easy for me to then take away that electron at a given point. Now, if I'm looking at and comparing, say, let's look at oxygen here and do a comparison next group over, and we're looking at sulfur, which is going to be right in this area. Notice that we have a huge drop in terms of the amount of energy. That distance between, even though it's in nanometers, it's going to make a big, big difference. That one's fine. Yurik, does that answer your question, or did you have any more to go with it? Now, the thing that we also have to consider is what's going to happen in the period or in the row. And again, my handwriting, I know it's a little rough. It's rough in regular setting, but it seems like it gets even more rough once we're on the computer, so I do apologize. So we have our group decreases down, and I'm going to use some shorthand, so please work with me because okay. Decreases because of distance. All of a sudden my pen is going haywire, but we'll work it out as we can. Now, the next thing, the period. What's happening in the row? Now, we have a continued trend, how where it begins, where it ends, because we have our alkali metal here and we have our noble gas here at the end, where it's extremely hard to try to pull away that electron. Again, the idea now, we're looking at energy levels that are approximately the same distance. So the next thing that we consider is Okay, if distance isn't the issue, what about what's happening with the nuclear charge? What's happening with the protons in the nucleus? Because as I add, again, the relationship we said, as I add more protons to the nucleus, I'm going to increase the attraction, the pull on those electrons. So if I'm doing a comparison between aluminum and argon, or aluminum and chlorine, whatever the case, aluminum has 13 protons in the nucleus, whereas chlorine has 17. That distance, and we found that with each one, it was actually a proportional amount. So it wasn't just this random, again, value. It increased in increments. So it's almost 3 to 4 times stronger because of those extra protons in the nucleus. This is going to cause those electrons on the outer ring to be pulled a lot closer to the nucleus. They're going to be able to fight a little bit more against the electron repulsion, which is going to allow them to be closer together. Now, this also ties in with the atomic radius, because again, as I add more protons, the radius of the atom is getting smaller, and this is what's causing it to hold on to those electrons more efficiently and more effectively. Do we have any other questions about ionization energy or the trends? Um, Test style question on Coulomb's law. Definitely. I'd actually prepared one. And this is one taken from an old AP exam. What I want you to notice is nowhere in the question does it actually say Coulomb's law. So let's take a look at it. Which of the following explains why the fluoride ion is smaller than the O2 or oxide ion? Your options are A, charge, B, fluoride has a higher electronegativity, C, fluoride has a greater nuclear charge, D, fluoride has a greater number of electrons, or E, fluoride has more nucleons and electrons. Which do you think the best option is? Or actually, a better choice, a better question that I would ask looking at this is, instead of looking at just which one is the answer, which ones can we get rid of? That's the key to a lot of these questions. If we can eliminate some of our distractors, then we can start to isolate what is actually correct. So, the question is basically asking us, based on Coulomb's law, why is it that the fluoride ion has a smaller radius than the oxide ion? Well, let's take a look. Of our options here, which seems like it shouldn't belong? Well, the fact that we're dealing with ions already, I shouldn't have to worry about the electronegativity, because the electronegativity is the ability to grab electrons or to steal electrons from other atoms. These are ions already, so they've already gotten the electrons that they needed. So I'm going to go ahead and mark B as not an option. It's gone. And I'm going to work on my spelling of higher next time. Now, are there others that we can really consider? Well, let's see. Looking at option E, fluoride has more nucleons and electrons than oxide. The number of electrons in this case would actually be the same. For those who are saying why, remember they're both ions. They've both already filled their octet, so the number of electrons wouldn't really matter. In terms of nucleons, that's just saying protons and neutrons. The neutrons have no effect here. So I want to go ahead and get rid of option E. It's also gone. Now, we also stated that when we look at why we have radius differences, it's very rarely about the electrons. We're usually looking at what is the effect on the electrons based on something else. So, part answer D is now out of the picture. So now we're here at this point. We're now looking at answer A and answer C. But which one is best? Fluoride has a more massive nuclear charge than oxide, or fluoride just has a greater nuclear charge than oxide? Well, let's look at overall how many not neutrons, protons does fluorine have? Well, fluorine has 9 protons. Oxygen has 8 protons. So A now goes out by default. Why? Because it's not that it has a more massive nuclear charge. It's not dwarfing it by much in this case. But it does happen to have a higher nuclear charge. With each question that you answer, you want to try to narrow it down as best as possible. Look at the wording, look at the phrasing. What are they asking you to figure out? And then start to isolate and knock out the ones that could not fit into that answer. One more? Sure. Let me pull together. If I did not say it in class, a very good book, even though it's based on the old exam, and I'm not, sponsored by them or anything. Um, the 500 AP Chemistry questions to know by test day, it goes topic by topic and gives you examples of what types of questions you could be asked based on the topic. So let's take a look at this. Um, I want to give you one that's similar to what you might get now. Uh, okay. Now, the question that I have, and again, I have it right here. It says, correct X ionization elements between atomic numbers 2 and 1118 include 1. There is a repulsion of paired electrons in the p4 configuration. 2. Effective at shielding electrons in the p orbitals of the same n than level. than each other, or 3 stable than unfilled cells. Again, I'll repeat that. Motion of paired electrons on the p electrons, the electron being the orbital of the same than each other, or filled orbitals subshells are subshells. Each of these statements, 2 only, 3 only, 3, just be statement and 2. Now, to look at it, electrons arranged. That 1 and 2 propulsion have similar to what we were talking about. I can go back to oxygen. I have electrons a higher amount at what happens to the ionization energy in 2 through 10 when we get to this point. All has to do with, sorry, so we can, so these test style questions. 2 copies of this book. I have to say borrow because I walked away and are still holding on to them. Are now at the assignments that were. Mac says, how could you do or negatives? I'm unsure of what, if you're mentioning protons and neutrons, we're for the overall charge. If there's an imbalance based on the information that's given to us, again, we have some form of information, but a shift in the configuration if all the arrows are, or we'll have more up arrows. Okay. Look at this. Let's go into a blank screen. So 1s is here. Three p and 3d. Acting up as I get up there. On the element on the periodic table, unpaired electrons I'm going to have, there will be more quote unquote up arrows are down. Now remember, the arrow is just letting us know that those electrons within that will have an opposite spin from each other, them to coexist without space. If I we'll go with nitrogen, element number 7. So our starting point is the lowest. The shell, we move. Why is it that we had, again, everything less repulsion and lower energy? So that gives them enough room to move apart than anything. Other than of them, we don't many are up and how many are down. Okay, we have 3 that are unpaired. Single bonds. Okay, because it's looking. Does that answer your question? Okay. Starting questions number 41, 141, and 134 for tonight. And question: microwave radiation has 1 centimeter, so it's about 1. Calculate the frequency and this radiation, and then this radiation. So, have and what am I looking for? First given, a 1 centimeter value. My frequency, and I'm trying to find the frequency. I need to use the following formula. New. Rearranging it based on new. Let's go ahead and start a little bit further. Okay. 3 times 1 centimeter. Get my. So, plugging into my calculator, into the eighth, 0.01. Now, with this value, this is now my new. Now I need to figure formula E my frequency. Keep having to clear the screen. Equals 0.26 times -34 times my frequency, which was 3 times 10 to the 10th. Energy for 6.626 -34 10 to the 10th. I came up with a 1.9. It down. My computer's acting a little. So 1.99. This is my energy value that I've calculated here. Okay, we have the energy for a single. It asks me to take this value, will be for Avogadro's number of these photons. We can use the information that we already energy associated. So one photon, oops, sorry, 1.9 times 10 to the negative 20, then 1.9 times. All right, I think we should be back up and running. Um, Giving it a second to come back up. It's kind of weird looking at myself on the screen. Okay, now to go back to where I just was. So we had calculated this energy and we had 1.99 times 10 to the negative 23rd joules of energy. That's a very, very small amount of energy. Because I wanted to figure out Avogadro's number of photons, the energy for basically a mole of photons, I multiplied the value that I had for the energy times 6.02 times 10 to the 23rd. Immediately, even before I plugged it into the calculator, I knew that these two were kind of going to cancel themselves out. And so I ended up with 11.97 joules of energy. Now, to give some perspective, and this is something again we're going to come to later in the year, to raise 1 degree Celsius is 4.18 joules. So this is about getting close to 3 times that amount of energy. It's not very much energy being released for even having a mole of these photons. This is why we say microwave energy is not as dangerous as it could be. It won't kill you, but it could eventually, by prolonged stuff, actually cause some problems. Also want to take a moment and look at question 140 on page 348. And I just want to give you some background on how these things can sort of be worded. And this will be the last thing. Hopefully, it won't try to cut me off in the middle of it since I originally set the time for 10. But if we're taking a look at it, it gives me that barium emits light in the visible region of the spectrum. If each photon of light emitted has an energy of 3.59 times 10 to the negative 19 joules, what color of visible light is emitted? So, again, looking at the given, now we're working backwards. Here we worked from the wavelength to the energy. Now we're going from the energy back towards the wavelength. The process still remains basically the same. So, and I'm going to go ahead and actually make this screen a little larger. So, if I'm taking a look at it, it tells me that the energy or the amount of energy is 3.59 times 10 to the negative 19 joules. This is my energy. So I need to work from energy and somehow end up at wavelength. The only thing that I can get to that will give me that ability is I have to go through frequency. So using E equals H nu, I'm going to solve and find the frequency. And then from there, I'll move into using the other formula to find the wavelength. So in rearranging this, I'm going to divide the energy by Planck's constant, which means nu equals 3.59 times 10 negative 1 9 all divided by sorry, giving it a chance to catch up. 6 2 6 times 10 negative 3 4. Sorry for the slowdown. 3.59 negative divided by 6.626 negative 34. I got a is 5.4 times 10 to the 14th. per second. Now, I want to take this out of full screen mode for a second. Still good. I just lost my work. Okay. Now, going back, I got 10 to the 14th. Now, that would get me the first leg of my journey, I guess you would say. So that would 5.42 times 10 to the 14th joules. Now I need to use my other formula in order to calculate the wavelength. So C equals lambda nu. I know C, and I know my new value. So C over lambda equals, oops, actually need to go C over nu equals lambda. So 3 10 to the 8th over 5.42 times 10 to the 14th. So immediately I know my value is going to be less than 1 because this value is much smaller than this. Plugged in. And I got as a final answer, I got lambda equals 5.45 or 5.4, sorry. Switch times 10 negative 7. So my answer in this really would be green. To address the question, Malcolm, I didn't forget about your question here. Naming compounds like HI and HBr. Immediately when you see H as the beginning of your compound, you should know that it's an acid, and we're going to go back to the three rules. Now, while that won't be focused on this test, it's going to play a nice role in the next unit, so I will address it quickly. So, let's see if it'll allow me to type, because typing is a little bit faster. Let's do it this way. This way, we can go ahead and make things the way we need them to be. Now, if I'm looking at a compound such as HBr, the immediate thing that should come to my mind is I have a hydrogen and a halide. The hydrogen is going to scream out to me, I need to look at the acid. So I need to look at what it means for a halide when I have an acid. The rule for halides is when naming an acid for a halide, it's going to be hydro as a prefix, the stem of the element, and then it ends with ic acid. So if I'm looking at this example, I have HBr, I'm going to have hydrobromic acid. This would be the same if I was looking at HI, in that it would be hydroiodic. Iodic acid. Now, what if I go a little bit further out from that? Well, if I have one that ends in just 8. So, again, hydrogen out front, but I need something that ends in 8. So, CO, 3. Now, first thing that I need to remember is I need to make sure things are balanced. So, here we go. If I have an 8 in here like carbonate, the next thing I have to consider is what's my stem, or how do I break down my stem? Again, the hydrogen out front still alerts me this is an acid. So, let's look at it. I have the carbonate ion. This is going to get a stem with ic acid at the end. I feel like this is working much better. So, as the example, I have the carbonate ion. I'm going to get carbon. I can spell, I promise. And I'm going to add ic acid to the end. This is going to be the same if I use, I don't know, perchlorate, ClO4. That means I'm going to end up with HClO4 is my compound. So this is my perchlorate ion. So it's going to be perchloric acid. The general idea is always going to stay the same. So that's why we want to make sure we're remembering the rule more so than trying to remember a specific example. If it ends in 8, ic acid. If it ends in a halide, hydroic acid. Last but not least, if we run into one that is similar to, it has, instead of an 8 ion, what if it has an ite ion? So we'll say H2SO3. Now, this is our sulfite ion. The hydrogen gives it away. This is an acid. So now we just need to put it in proper perspective. So if we're naming one that ends in "ite," like the sulfite ion, what we're going to do is we're going to have the base or the stem with us at the end, us acid. So to give the example, the sulfite ion would be sulfurous acid. If I were to have, oops, the nitrite ion, that would be NO2. I would have nitrous acid. Oops. Any other questions before we begin? Or before we end, I'll say. If no other questions are coming up, I'm going to say we will end it here. Um, okay. How will the test be presented? Um, there are a total of 20 questions. 18. Oop, sorry about that, Mac. Deepest apologies. There are a total of 20 questions, and there are two of those are FRQ. There are some that deal with empirical formula. There are also some parts that are going to deal with your PES and your mass spec graphs. So reading and interpreting the data and then doing the calculations based on that are very, very important things to be able to do. So we're going to get a good mix of all the things that we've covered, including the labs. So there's a reason why I've been asking and asking for clarification. Yes, limiting reactant will also be on there too. Now, you'll notice that a lot of these can sort of work together, so don't think that it always has to be a separate question. It could actually just be another part. It could be part of another question where we're doing some type of calculation. But yes, limiting reactant will be present there as well. I mean, okay. Any other questions? Is stoichiometry is spelled right? Yes, unfortunately, we can't get rid of stoichiometry for the entire year. We're going to keep coming back to it in different ways. The more you're exposed to it, though, I believe the easier it's going to get. You'll start to see how it connects, how we can use it to find out all information. 5, 6, and 7, no. The information that we covered really is just from two main chapters. It's from chapter 3 and 7 and a little bit of 8, the PES at the beginning of 8. Okay. Give a couple more seconds for any last minute questions. I'll probably, before letting this post to YouTube, I'll probably edit some of the long pauses out just to make it a little bit easier for those who may watch later. Um, but I think we have reached the conclusion for the night. I appreciate you all coming out or signing on. Next time I'm going to see if we can work it out so I can get a little bit less glitch with my writing, so it's a little bit easier to follow, and hopefully we won't have anything to shut down on us again. Um, Again, any questions that you may have, feel free to email me. Um, I will be up for a little bit working on some things, so we'll move on from there. I wish you all a good night, happy studying, and I will see you all tomorrow where we get this all taken care of.